One of the major challenges in NLP is about knowing which approaches or architectures will work for a particular problem on a particular dataset before implementing a system. In our paper about transportability, we examine how the same system performs in different domains and for different tasks, while updating parameters by training the system on the new domain each time. We show different architectures perform differently based on the similarity of the data, and that in general, performance is worse as distance between data increases. In our experiments, this distance is defined as cosine distance, KL divergence, and lexical divergence. We formalize transportability with a lightweight mathematical framework to support further formalism and experimentation. We hope this may allow insight into which approaches are likely to work well before implementation, as well as point towards why particular approaches are effective in particular contexts.
This work is an implementation of temporal semantics. It's based on FACOC, which is our natural language semantic system. Our target is the fracas test suite. We start with abstract syntax trees, then we interpret them using a Montegovian semantics plus dynamic semantics. This gives us logical formulas in a type theory. And then we check if these formulas meet a proof or not, and we do so using the Coq proof assistant. In this paper, we add support for temporal semantics to the system. How do we do that? Well, you will have to read the paper to find out. But just to give an idea, and perhaps to catch your attention, here are a couple of examples from the test suite that I'll let you read on your own.
I'm James Gung, presenting our paper entitled Predicate Representations and Polysemy in VerbNet Semantic Parsing. Suppose we want to understand the semantic roles of a relatively uncommon verb like tiptoe. We know what they should be for a similar verb that's much more common, like ran. Can we infer from this that tiptoe might have similar roles? How can we apply this intuition? VerbNet is a lexicon of English verbs that groups verbs into syntactically and semantically coherent classes. It's possible to substitute a verb in a sentence with any other verb in the same class and produce a syntactically coherent sentence with the same thematic roles. And look, tiptoe's in the same class. Now we know tiptoe is in the same VerbNet class as run and can make a better guess about its semantic roles. We can also learn from the many other verbs belonging to the same class. Can this intuition be applied to other semantic role labeling formalisms like prop bank? In this work, we investigate two ways to apply this intuition to semantic role labeling. First, we use VerbNet classes as predicate-specific features in a semantic role labeling model. Second, we investigate a multitask model where we can jointly predict VerbNet classes for polysemous verbs as well as their semantic role labels. Come check out our work.
An emerging line of research in explainable natural language inference is the creation of datasets enriched with human annotated explanations and rationals, which are then used to build and evaluate models with stepwise inference and explanation generation capabilities. While these explanations are used as ground truth for the inference, there is a lack of systematic assessment of their consistency and rigor, with the risk of introducing biases within the models. Therefore, to provide a critical assessment of these resources, we propose a systematic annotation methodology, which aims at quantifying the logical validity of human annotated explanations. We validate this methodology on three popular datasets for multiple choice question answering and textual entailment. The application of the framework reveals the surprising conclusion that most of the human annotated explanations, while appearing coherent at the surface, actually represents logically invalid arguments, ranging from being incomplete to containing clearly identifiable logical errors. The study, therefore, reveals that inferential properties of explanations are still poorly formalized and understood, and that additional work in this direction is necessary to improve the way we build explanation-annotated corpora for natural language inference.
Hello, I'm Natalia, and I'm presenting the paper about automatic assignment of semantic frames in dialogues. This paper is a part of the research project called ADRZ. One of the goals of this project is to capture and interpret verbal team communication in disaster response scenarios and use the extracted runtime mission knowledge for mission process assistance. For example, given an utterance, we would like to identify actors, mission objects and locations, and also the intent of the utterance. In our paper, we try out frame semantics as a meaning representation framework. We retrain one of the existing state-of-the-art frame classifiers called Puffybird on a small dataset from a novel domain. We study the effect of sampling from unrelated domain and experiment with lexical and discourse features. We also evaluate the models using a performance metric designed for imbalanced data. For more details, please come and see our poster. Thank you.
My co-authors and I wanted to find out whether the distinction between causative and non-causative sentences could be learned by contextual language models, especially since causativity is not usually marked on the surface in English. We set up experiments with 3 different language models, BERT, XLNet and Distilbert, and we created 3 different data sets in which sentences were either causative or non-causative, they were either transitive or intransitive, and one of the datasets even included alternating verbs that are sometimes causative and sometimes non-causative. The classifiers that we trained were surprisingly accurate, with scores between 83 and 95%, but when alternating verbs were included in the data, as you can see in the lower right corner of the screen, the performance dropped slightly for all language models. In general, causativity tended to be represented in the higher layers of each model, consistent across all datasets. And we found that each model can be reduced to the 10% of its neurons that are most correlated with causativity, with only minimal changes to the classification performance. So we did find some causativity neurons in these language models. Please come talk to us or read the paper if you're interested in our work. Thanks.
Hey all, this is Stowe and I'll talk in short about our paper for temple tagger for the voice assistant domain. So, what is a temple tagger? For example, in a command, book the room for tomorrow from 9 am for 2 hours. It has several expressions indicating date, time and duration. Those have some absolute values with respect to the reference time. The tagger extracts these expressions and normalizes them in some standard format. But the extensive work on the existing taggers is mostly for the news domain, and not enough data is available for the voice assistant domain. So does it take a major effort to adapt a tagger to a new domain? For that, we apply transfer learning on a neural tagger from the news data and fine-tune it on our limited voice assistant domain data. We also show a domain-specific normalization, and we find that major improvement comes with only 10% of target data, which is quite higher than some existing state-of-the-art taggers. So to know more in detail, join us during our poster session. Thanks.
Unscoped logical forms of episodic logic were recently introduced as a semantic representation that captures the core semantic structure of episodic logic while staying close to the surface language to ease annotation collection and automatic parsing. In this work, we present the first official data set of manual ULF annotations and a baseline parsing model trained on that data which exploits features specific to ULF in order to outperform existing semantic parsers. We modified the cache transition system with 2 additional types of actions that exploit features of ULF. One is the token and part speech-based symbol generation. For example, from the verb ran, we generate the ULF symbol run.d. The other is promotion-based constituent modification. For example, the reification of the noun dog with the kind-forming operator k. We then train a model to predict actions in this transition system using LSTMs for the sequences of words, symbols, and actions. If you'd like to know more, please come ask us about our experiments constraining the decoder using the ULF type system, how our parser fares against existing semantic parsers without ULF-specific designs, details about the transition system and model, or experimental results.
Hello, my name is Eric Holgate, and I'm here to present my work with Katrin Eric entitled Politeness, You Simpleton, retorted Mask, Mass Prediction of Literary Characters. Neural language models have led to huge improvements across many tasks recently. These models compute embeddings for words and word pieces. But when we describe the semantics of a sentence, we talk about the entities and events and their relations, not about the words. In this paper, we address the highly challenging task of guessing from a sentence in a novel which character is being talked about by learning embeddings for entities. Our model trains a binary classifier that says, for a masked mention, is it this character or not? The character embeddings are input into the classifier, as well as the embedding of the sentence. We find that when continuously trained, entity embeddings do well at masked entity prediction, even when examples are constructed from Wikipedia summaries instead of the novels themselves. We additionally probe these embeddings to reveal that they encode considerable information about the traits and characteristics of the literary characters. Thank you, and we look forward to talking with you more about this work.
Tuning deep active learning for semantic role labeling. Active learning allows us to reduce annotation requirements for supervised models by choosing only the most informative instances to annotate, according to the model itself. This can be challenging when using neural networks, as their outputs are not accurate estimates of confidence. Since semantic role labeling involves labeling argument spans for potentially multiple predicates in a sentence, it can additionally be challenging to aggregate the numerous decisions into a single score. We apply two ways of aggregating scores across predicates, combined with two methods of estimating certainty: the neural network's outputs and an efficient dropout-based Bayesian active learning by disagreement approach, tuned for SRL. We compare these with three baselines with respect to reducing the number of annotated sentences and predicates. Although the standard methodology for SRL corpora creation leaves much room for improvement by even passive strategies, we show that active learning can provide significant reductions of both sentences and predicates, requiring half as many sentences and a fifth fewer predicates to achieve a reasonable performance.
Hello, my name is Kevin Stowe, and I'm going to cover our work, Semlink 2.0, Chasing Lexical Resources. Start with a problem. We have a series of lexical resources, each with its own strengths and weaknesses. These resources comprise a series of verbs, verb classes, and verb senses, which can be linked to each other to best utilize each resource. However, when the resources change, these links then become invalid. Consider if a verbnet class splits, we then have a series of mappings which are no longer functional. In this work, we develop a method to computationally assess each of these broken links and fix them where it's applicable. In cases where they can't be fixed, we can then pass them to annotators who make the right choices. In some cases, the links cannot be fixed and are then removed. This work then develops an updated mapping between all four of these resources via both automatic and human updates. We apply these mappings to corpora to double the amount of annotated sentences from the previous Semlink, and we release our code and resources in the hopes of improving future automatic updates to Semlink.